Okay. I don't know when he's gonna have his class taken. Just do the more review. Won't be here for a week. All right, let's look at number 1, starting with differential equation. This is page 25. Okay, let y of t be the temperature in degrees Fahrenheit of a cup of tea at time t minutes. Okay, room temperature is 70 degrees, and initial temperature of T is 180 degrees. T's temperature at time T is described by the differential equation, dy dt, with initial condition, okay, y of 0 equals 180. Use separation of variables to find an expression for y in terms of T, where T is measured in minutes. Okay, so separation of variables. If we see time, in this case it's T and y, so time is going to be our independent variable and y is our dependent variable. But first, I like to get everything set up, see if I can cross multiply. Again, anytime you see parentheses with a differential equation that's presented to you, they are there to help you out. Okay, if you distribute, you lose that separation that they're already trying to help you build. So don't expand. Right, parentheses are going to be your going to be helpful with your next step. Okay, so I like to get my denominators out of the way, so I'm going to cross multiply. Okay. All right, we have my dy dt are locked in. What's out of place? Yeah, y minus 70, right? If I want to bring the y over to the left to group it with the other y's, I got to bring along the minus 70 as well. Right? Got to go all together. Okay, so after I separate the variables, I just rearranged it to help us maybe see visually what steps to take. Here, the left side looks like we can go through use substitution. Right, let the u value be the denominator. Looks like it's going to match up nicely with natural log, and you know that this u value is not going to produce anything other than the 1. And so this over here, this integral of 1 over u du, you know this ends up being natural log absolute value of u, and then replace the u back in terms of y. Okay. Okay, power rule here. You know the negative 0.1 is going to stay. The integral of 1 becomes t. All right, so the calculus is completed. We now have 2 more things to do. We got to solve for c, and we have to get that y by itself. So typically I like to, if I see natural log in the problem, I tend to wait a little bit later to solve for c, but you're welcome to solve for c at any point as soon as it comes up. I'm going to raise both sides with e as the base. Yes.
Did the u value, the final derivative of it, why wasn't it dy? Why didn't like y turn into dy?
It does. I went du over dy, but I could have done du is equal to 1 dy, and then solved it that way.
Same result.
Same, yeah, yeah, yeah. You would have gone to the same thing, right? Dy equals du, and then gone that way. Yeah. Okay. We know e to the c is just one big constant. I can pull that constant in front, and then the absolute value bars can drop because the plus and minus will be taken in by that c value. Mm-hmm. Okay, which part? Oh, t, yeah, you're right. That should have, I did not copy that over. That should have been there. Okay. All right, so now this feels a little bit cleaner without the natural log, and then on the right side cleaned up a little bit nicer. And now I can just solve for c. The order pair that's provided for me is 0, 180, 0 in for t, and 180 in for y. Okay, anything times 0 is 0, e to 0 is 1, so that's just going to give me c. C is equal to 110. Once I have my c value, I can go back and make that substitution. And then I can finally solve for y. Okay, so this equation is going to tell us what the temperature of the T is. at a certain moment in time. So that goes to part B. How hot is the T after 10 minutes? We have our equation that will tell us that. So just plug in. Use your calculator. If the tea is safe to drink when the temperature is less than 120 degrees, at what time is the tea safe to drink? So we can just basically use the same equation. There's no calculus here. We can plug in 120 in for y and work backwards to see at what time will the temperature drop down to 120 degrees. Okay, so algebraically, we're going to solve for t. So subtract the 70, divide the 110. Let's get that e exponential function by itself, and then we can worry about the rest. All right, I want to solve for t. What I can do is I can take the natural log of both sides. Bring that exponent down. Okay. Once that exponent comes down, the natural log of e goes away, because natural log of e is just 1. And then finally, we'll just divide both sides by negative 0.1. Okay, we know that 7.8 minutes is when the temperature drops down to 120 degrees, so anything after greater than 7 minutes, 7.8 minutes. Okay, closing time at shopping mall does not magically empty. They are customers completing sales and employees having to go through closing procedures. In the table below, t equals 0 represents the announced closing time of the mall. Negative numbers represent time in minutes. For closing, positive number represent the time in minutes after closing time. Total number of people in the mall is strictly decreasing, twice differentiable function p. So smooth curve. Oh, sorry, thanks. A curve is always decreasing. Values of P of T is, at selected times T are given in the table. So this represents 25 minutes before closing. This is the number of people in the mall. 15 minutes before closing. At closing, there's still 175 people. But then as time goes on, more and more people are leaving. Some of the employees, people closing shop, are trickling out of the mall. Okay, use data to estimate P prime of 5. So we know we want to find the rate of change at which people are leaving 5 minutes before the mall closes. So we can use slope, right? Take the closest order pairs. Use your calculator. This is change in people. We're changing minutes. So units of measure will be people per minute. So this tells us 5 minutes before closing, use data in the table to evaluate the definite integral from -25 to 30 of P prime. Use correct units to interpret the meaning -25 to a 30 P prime in the context of this problem. Okay, now this is not P prime, so we're not going to do the area under this graph, right? But what we can do is we can use first theorem, right? First theorem. If I take the antiderivative of P prime, what does that become? What do you think? Integral of P prime will rise up to what? Just P of T, yep. And then we can just plug in upper and lower bound, right? So P prime rises up to P. So P of 30 minus P of -25. And then 25, and then now we can read from the table, right? P of 30 minus P of -25. And then we can also use this number to interpret what's going on here. P of 30 is the number of people in the mall, 30 minutes. This is number of people in the mall 25 minutes before closing. So if I get this number, what does this number tell us, you think? Okay, good. So to people who've left, also another way of saying it is that the change in the number of people in these time intervals. Yeah. Okay. For t between -25 and 30, the approximate average number of people in the mall by using a Riemann sum with 4 subintervals. Does this approximation overestimate or underestimate the average number of people in the mall over this time period? Okay, explain your reasoning. So average value theorem is 1 over b minus a. Okay. My a value is -25. My b value is 30. Okay, so this coefficient is going to stay. What we're going to do is we're going to use Riemann sum to replace this value. Okay, so we'll find area under the PFT graph, width times height for each of our subintervals here. Okay. All the widths are going to be positive values, right? -15 minus -25, 0 minus -15, 10 minus 0, 30 minus 10. Okay, width times height, width times height, width times height, width times height. And also it's asking for whether it's an over or underestimation. We know our graph is strictly decreasing, so we know our graph is going to be sloping downward. And if you just try to do any right Riemann sum, you can convince yourself that all your rectangles are going to sit nicely below the curve. It's going to be an underestimation. Okay, questions? So width times height, add up all the areas of rectangles, but I got to still make sure I include that 1 over b minus a, that 1 over 55. This will give me the average number of people at each in that time period, or over this time period. Okay, between -25 and 30, the function p models the number of people in the mall. P prime, the rate at which people are leaving the mall, based on the model. How many people were in the mall 5 minutes before closing? So we like to use this formula here. Anytime I'm looking for a final value, I have a starting value plus displacement, right? So if I want to find out number of people 5 minutes before closing, I can start off as, let's see. Yeah, because these data are set in stone, right? We know that these are exact values, but now that we have a function that's going to allow us to bridge that gap, find out more detailed information between these given values, we know that we can start at -15 and then we can figure out the accumulation of what's happening from -15 to 5 to -5. Okay, so that's why we start at -15, because that's a known value that we can use. And then we want to figure out, between -15 and -5, how many people have left the mall. So if we know how many people were in the mall here and how many people have left, we can figure out how many people are still in the mall 5 minutes before closing. Okay, so this can go in our calculator. Integral from -15 to -5. Plug in your P prime. This will do the job of accumulating the number of people in that time, in that 10-minute period who've left. And the number is -191. So 420 minus 191, 228. Yeah. Question? Yeah, the -15 came from the fact that we have, we know that 15 minutes before closing, there's 420 people in the park, in the mall. So we want to figure out how many people are in the mall at 5 minutes before closing. So we basically want to choose the closest known value and then bridge the gap to 5 minutes before closing. So that's why I'm picking my starting or given value at 15 minutes before closing. Okay, any questions? All right, since we have additional time, why don't we go back and, I don't know if you guys done this already, but we can go back and do page 23 and 24. Since that was your homework, but I didn't get to do this in class. Let's see. I'm going to skip down to, I think this is mean value theorem. Oh, I think these are pretty straightforward. I want to go down to part C on page 23. Have us practice through these types of setups here. Yeah, on page 23 here. All right, so this is set up where I know the antiderivative is going to bring me up from G double prime to G prime, but along the way, I know I have to keep track of what happens with that 1 minus 3x. So I'll go through use substitution here. Okay, push the negative 1/3 in front. Okay, we know G double prime is going to rise up to G prime. Okay, before the bounds come into play, let's make sure the variables are matching. Let me bring the original variable back. Okay, so now that I've taken the antiderivative, G double prime became G prime. I'm also keeping track of my coefficient. I can now work in my original bounds. Okay, insert my upper bound in for x minus, do the same thing for lower bound. And then our table of values above can help us make our final substitutions. So -3 in for x, I get 1 minus 3 times -3, which is 10. And then 1 minus 3 times -1, that's 1 plus 3, which is 4. G prime of 10, look at your table. It's going to be 0. G prime of 4, look at your table. It's going to be 5. Keep track of your negative 1/3 in front. 5/3. Yeah, so I would say that don't worry about flipping the bounds unless you're trying to read the graph. You're trying to read the graph from left to right. Then I prefer to flip the bounds because then your positive is above and your negative is below. But if it's just something where you are doing things from a calculus perspective, then it doesn't really matter. I mean, you can flip the bounds. It just feels like an extra step that's not going to make things easier. Right. But yeah, you're welcome to flip the bounds anytime you want. Just have to make sure if you do that, that you change the sign in front. Okay, page 24. Okay, 24D is L'Hopital's rule. Part E is product chain rule. Let's go down to F. I want to do, let's get some practice with differential equations here. So part F. All right, so I prefer to have everything x's and y, so I'm going to rewrite this y prime as dy dx. I'm going to force that over 1 here. Cross multiply. Okay, separate the variables. The only thing out of place I see is this 1 minus 2y. I'll move that over, divide that 1 minus 2y over. Right. Use substitution. There's going to be some leftover coefficient we got to keep track of here, though. Okay, so that's going to be the result of that left side. The right side is just pretty easy here. G double prime will just go up to G prime. Nothing that we have to do in terms of use substitution. Okay, let me reset here. Okay, calculus is done. I want to solve for y. I find that it's easier if I can get this. Yeah, I want to involve eventually base e with natural log, but this -1/2 is kind of getting in the way. I'm going to move that -1/2 to the other side, so multiply everything through by -2. All right, e exponentiate both sides. We want the e and natural log to pair up so that we can get these to go away. E to the c is just one big constant. Hold that constant in front. Drop the absolute value. Yeah, I think I solved for c in a different spot on my key here. I'm going to solve for c here before my fractions come out. Okay, 1 in for x, 3 in for y. Okay, g prime of 1 is 9. So -2 times 9, -18. I can bring that 18 back up to the top. Okay, let me insert this back into my equation here. divide everything by 2, multiply everything through by 1/2. And then use the oh, I'm sorry, I plugged in the wrong value here. I should have plugged in 1, 0. I don't know why I plugged in 3. Okay, sorry. This should have been the 1, 0. My bad. That threw things off here. So I plugged 1, 0 in. Power 3 is 7. Oh, 14. 2 times 7 is 14. Okay, so this is my equation before I started plugging in that 3. Mhm. I'm sorry? Uh, yeah. You can leave it in any form. Any of these forms is fine. All right, thank you.